Vladimir Zekovic, could you please share your screen, share your presentation? We have 2 minutes until start, just to be prepared. Once again, I would like to ask all participants who are not presenters to switch off their cameras and turn off their microphones, because we are all panelists now. And just to prevent any noise. Thank you. Dear ladies and gentlemen, dear colleagues, welcome. This is the second session in a row of the second day of our Serbian Astronomical Conference. Let me introduce myself. I am Angelika Kovačević, and this is the continuation of the previous session titled Stellar Physics and Physics of the Interstellar Medium. We will have 3 very interesting lectures, and I would like to introduce, and it is really my great privilege, one of the best PhD students, Vladimir Zekovic, his work in collaboration with his mentor, Professor Bojan Arbutina. The work is quasi-parallel collisionless shocks, revealing the nature of cosmic particle accelerators. So Vladimir, please start. You're welcome.
Thank you, Angelika, for this introduction. Can you hear me?
Yes, of course.
Okay. First of all, thanks to organizers for giving me this opportunity to talk about shock waves. So this is practically the work of not just of our team, but of the other teams all around the world. So today I will give a talk about quasi-parallel collisionless shocks. These type of shocks, these collisionless shocks, are actually present everywhere in space. So we can find them at supernova remnants, supernova explosions, AGNs, Earth's bow shock, pulsar nebulas, as you can see in these pictures. So what is, at the first place, what is the shock wave? So we have the wave. The wave is the perturbation which travels with the velocity of sound, for example, in a fluid. The shock wave would be the perturbation which travels with the velocity greater than the velocity of sound, or the typical velocity of that fluid. So, for example, if we take a look at the sea waves, water surface waves, we can see them as sine waves, but actually they could be also the Salton structures, but once they come to the shore, to the shallow water, they start to steepen and rolls and collapses. So this is the moment when they are becoming the shock waves. So actually we see these patterns, as you will see, also at phase space of collisionless shocks. So it's a very clear picture for fluids. It is water, the medium that mediates the shock. It is the air, for example, the sonic boom. So what about space? In space, we have a different kind of medium. So the mean free path of interstellar medium particle is very large. So actually the plasma is collisionless, so there are no Coulomb collisions between particles. And all interaction is governed by the electromagnetic instabilities, which are excited by particle motion themselves. So for example, if we use the MHD theory, we can model the shocks, we can model different kinds of plasma interaction, but we model it on the scales which are much larger than, for example, ion or electron gyro radius scales. So actually we can have these upstream and downstream conditions, and we have this infinitesimally small transition layer. Actually, in reality, it is not such. this transition layer, it have some finite width and have some structure. In order to resolve the structure, we use different kind of simulations. We use the kinetic simulations. We solve the kinetic equations combined with electromagnetic field. So not only the simulations, but some other methods. As you can see in these pictures, this is the real shock, how it looks like, or at least really in the computer reality. So we have the upstream of a shock wave, we have the downstream. This is the shock transition region. So as you can see, it is very turbulent. And the bottom top plot shows the particle trajectories. So as you can see, they are very chaotic. So actually what we use is the linear theory by which we model the interaction of the colliding plasmas and the instabilities that are growing. We use nonlinear theory to describe the moment when these instabilities becomes nonlinear and starts to modify the plasma flow. And at the end, we use particle in cell simulations, kinetic simulations, as an experiment to confirm or even calibrate the equations from the theory. So actually, the linear theory shows interesting results. For example, we are getting the dispersion relation for right and left circularly polarized waves. And these waves are very resonant, as you can see. If we have two plasmas colliding with comparable densities, this density ratio eta is given here, then we have that instabilities, the waves which are driven, are indeed very resonant. This red line vertical denotes the resonant position. What does this mean? This means, for example, if you have a beam of ions coming here from the left to the right, just small note, this is the velocity phase space, it's not the physical space. So on the x-axis, we have the longitudinal magnetic field directed axis, and here on the vertical axis, we have the velocity along the magnetic field. So the magnetic field is aligned with the x-axis. So actually, the beam which is coming from the left is going to the right. It encounters this wave, circularly polarized wave. So it starts to interact, and for the very resonant wavelength, as you can see, there is a strong interaction. So almost all particles are reflected. So it is a very narrow band of wavelength here. To show how it works in practice, we use the kinetic simulations, as I said. These are particle in cell simulations. We use ions and electrons treated as particles. We move them on the grid. We define electromagnetic field of the grid, solve find currents and densities, solve Maxwell equations, and then again in the next step we move particles. So only force which is acting here is the Lorentz force, nothing else. And we can also accelerate this kinetic simulation by using the hybrid code. The hybrid kind of simulation treats electrons as a massless fluid. So actually, we can speed up the simulations. So let's take a look. This is an example of simulation. We have two cases, completely perpendicular shock. What does this mean? This means that the magnetic field lines are perpendicular to the direction of a flow. If you take a look at the parallel shock, it is a case where magnetic field lines are aligned with the flow of plasma. So actually what we do, as you can see here, there is this bottom beam of ions and electrons, which is coming here from the right and going to the left. Once the beam encounters this left wall, it is reflected. So we just have the two plasmas that interpenetrate each other. In the overlapping region of where the two plasmas overlap, we have the growth of different kinds of instabilities and fields. These plots are the density profiles, and these are the transverse magnetic field profiles and longitudinal electric field. So actually for the perpendicular shock, we would expect that the ions are starting to gyrate, so they have the gyro motion. So we can observe this even in the first step. But for the parallel shock, the particles are really sliding along the magnetic field lines. So there is no interaction here yet. Once in very few steps, we have that the first loop is formed. It is at perpendicular shocks, and we have this maximum formed in magnetic field and electric field, and this maximum is actually our reformed shock or reformed potential barrier, which starts to act like this left wall. So it really starts to reflect the particles. So as you can see now in this animation, it repeats periodically. So this is the reformation process, the shock reformation process. As we can see, this shock reformation leaves this soliton structure. We modeled this by nonlinear theory using solitons, and it very nicely agrees. It is a work in progress. And as you can see, for the parallel shock, nothing is happening. We have the growth of this wave, but there is no significant interaction here. If we zoom out a little bit, we can see the interaction for parallel shocks starts later, when once this wave has grown to the amplitude of a longitudinal magnetic field. So it is a very low amplitude, but because it is resonant, the interaction starts, as you can see now. The beams are decelerated and they are merged, and there is a separatrix point here. So actually, this is the point when the shock formation has started. And the shock is formed, and that is the initial process. As we can compare this to 2D simulation runs, we can see these are the same plots. This is the velocity phase space. These are the density map. This is the density profile, magnetic field map, and magnetic field profiles. So you can see that this is the downstream region, the upstream region. So at early stages, you can see these viable instabilities. These are just the transverse waves, electromagnetic waves, and they are governing the shock formation and reformation process. And at later stages, once these resonance instabilities has grown, they overtake the reformation process. This is the case of unmagnetized shock, or for example, weakly magnetized shock. In that case, we have these viable instabilities which are going upstream. They are forming current filaments. These filaments later merge and form the shock wave. This is the case of a quasi-parallel magnetized shock as before. But here we have very large scales. On such large scales, we have a formation of these filamentation instabilities in the downstream at the shock. And in the upstream, we have the Bell's type instabilities driven by cosmic rays. This is for comparison. This is how the shock looks for different magnetic field orientations. For example, here on the top graph, the magnetic field is completely aligned with the flow. So we have the very turbulent shock. As we get to the case of perpendicular shock, we are getting this very sharp transition. So it's almost like MHD case. The density profiles are given here. The blue lines denotes the quasi-parallel shock, and the red lines the quasi-perpendicular shocks, as you can see. From these spectral particles, we can see actually that these spectra are showing that quasi-parallel shocks are accelerating particles more efficiently. So you can see these non-thermal tails here, but perpendicular shocks have strong suprathermal tail, but by my opinion, they will eventually start to accelerate particles, but it's very, very complex picture. If you take a look at the case of quasi-parallel shock spectra, right at the shock interface, you can see these non-thermal ions here, and you can see this thermal-like distribution. I'm telling you it's thermal-like because the Maxwellian is presented with the blue color, but this spectra nicely fits the red color, which denotes the kappa distribution function. This kappa distribution is typical to the plasmas which are out of equilibrium. So if you can see on the bottom graph that how this distribution evolves. Actually, if you're going from the shock towards the downstream, you will get the Maxwellian distribution. And at the shock, the shock reformation process is ongoing. You have this kappa distribution, which implies the non-stationary regime. Particle acceleration actually works in this way. We have thermal particles which are thermalized in one-step mechanism, right at the shock overshot region, at the shock cross potential. And we have, for example, non-thermal, suprathermal particles. These are the particles that are reflected once or twice from at the shock, reforming shock barrier, the green lines, and they have some kind of larger energy, higher energy. And this blue line denotes the non-thermal particles, which experience multiple reflections. So actually, they are diffusive shock accelerated particles. This is the example of the simulation. We have few ions coming from the right to the left. Some of them are becoming thermal. Some of them experiencing one reflection, actually two reflections, becoming superthermal, and those that experience multiple reflections are actually diffusive shock accelerated. So this acceleration is due to different velocities of this upstream instability, which is incoming, and then it is slowed down at the shock. So actually, like we have the two approaching balls, and like a ping pong effect. This also appears in peak simulations, and you can see this is the shock wave. These are the particle trajectories in the phase space, and these are the resulting spectra. So to conclude, the formation of quasi-parallel shocks is indeed triggered by resonant ion stabilities, which provides the transverse magnetic field on which will stop, actually slow down, decelerate the plasma flow. Once the deceleration has started, it induces the growth of magnetic field and electric field, which further induces the further deceleration of the flow of the ion beams of the plasma beam. So actually, we have the formation of nonlinear soliton structure. It is observed before, it is modeled before, but these days we are having the exact analytical solution to the shock reforming process. So it's very interesting because we expect that the shocks are completely chaotic, some kind of process which which disorders the plasma. But yes, it is like that. But it is through the very finely tuned resonant processes. So actually, we have this particle thermalization going in one step. We have the formation of current of reflected ions, which are exciting the non-resonant instability ahead of a shock. This instability ahead of a shock actually is responsible for the suprathermal population and for acceleration of particles in the DSA by the DSA mechanisms. So thank you for listening. If you have any questions, please ask. Also, if you have any comments, they're very welcome.
Thank you, Vladimir, for this very detailed and very nicely prepared talk. So we can now proceed to questions. Of course, as you can see, you cannot raise the hand as a panelist, but you can unmute yourself and ask the question. So I would like to ask, is anybody in the audience has a question for Vladimir for these really nice results, simulations, maybe comments, also the comments from the mentor and other collaborators from a group where Vladimir Zekovic is working is also welcome. Yes, we have something through the chat. Tomislav, you can unmute yourself and ask question aloud. Tomislav? Okay, I would read on behalf of Tomislav his question.
Yes.
Did you consider including effects of rotation, such as shock, in binary systems?
No, actually, these simulations are on very, let me say, small scales. But there are people doing, I know for them, they are doing simulations for example, I think they're simulating accretion disks, but for this purpose we are doing only the very narrow width simulation boxes. So this is because we don't have much computational resources available, but even if we do, you can always increase the resolution. So this is the problem, because we are simulating only one small region around the shock, and it is very narrow. So to increase the width, to introduce some kind of rotation or different motion, it is very computationally demanding. So that is the problem. But thanks for suggestion. I will take into account, certainly.
We have a question, another from Tomislav. Is your code available?
Yes, this is completely freely available code. You can download it on the GitHub. I will write the address in the chat section. So it is the standard code. It is called Tristan MP. So it's freely available. And also you can mail me. I can send you by mail. It's no problem.
Thank you. Any other question, comment? Maybe comment from the mentor. And we have another message from Tomislav. Thank you. I was previously using Pluto code.
Yes, the Pluto code is the MHD code, and this is the particle itself code, so it is on much smaller scales. This means that it resolves the different kinds of plasma scales, plasma oscillation scales, particle gyroradius scales. So the Pluto code is MHD, and it is on the much larger scales.
Thank you once again, and thank you, Tomislav, also for posting nice questions. So we are moving to other speaker. It is also, I'm really glad to introduce our early career astronomers, excellent young scientists, Attila Čeki, Olivera Latković, and also excellent PhD student Sanja Lazarević. And Attila Čeki will present statistics of the largest sample of late type contact binaries studied so far. So Attila, you are more than welcome.
Thank you.
On the last talk, and also I would like to thank Tatiana for posting the question. And I am really glad to introduce you our dear colleague, Professor Istvan Vince, who has been professor at Department of Astronomy for many years, and in parallel, research professor at the Astronomical Observatory Belgrade. Professor Vince will talk about some gas stream velocities in UU-CACS close binary star. So Professor Istvan, you are welcome to share your presentation. Hello, Professor Istvan. Professor Istvan, hello, can you hear us, please? Vladimir and Stanislav, can you unmute? Can you send invitation to unmute Professor Istvan Vince? We will wait just a little bit. Professor Istvan, can you hear us? Stanislav, did you send invitation?
Yes, I did.
Mm-hmm.
We are just waiting because there are also two profiles, but
Mm-hmm.
I asked to unmute on both, so we are just waiting.
Thank you. So we will see. Just wait a little bit.
Yeah. Okay.
Hello, Professor István. Can you hear us, please? Professor István, can you hear us? Can you turn on your camera? Professor István, can you unmute yourself, please?
Hello.
Hello, Professor. Welcome.
Okay.
So please, you can share your presentation now.
I have Zoom. I have no Zoom. I could not hear.
We can see that you have that you are logging in Zoom via two devices. So one device is unmuted, other devices is muted. So can you just turn off one of your logins? Stanislave, can you expel login which is muted?
Yes.
Yes, please. Just not to make problem here. Okay, thank you. Professor Vince, are you there?
Yes, I am here, but yeah, okay.
Now it's okay.
Oh, let's start.
Yes, let's start now.
And my presentation, just a moment. That one. Can I start?
Yes, please, you're welcome.
So,
Perfectly. Please start, yes.
everybody.
All is working.
You look at a close binary star, and only a few words about that star. So it is about 10 magnitude star, like a complex binary system. We have been studying it since 2008. Its orbital and physical parameters we acquired from photometric and spectroscopic measurements. Based on these results we achieved, we can imagine one simplified picture of the system. Here you can see that the system is consists of two stars, a disk and a gas stream. The donor star, this one, fulfills its Roche law and lost the matter through the first Lagrangian point, forming a gas stream. This gas stream forms an optically thick accretion disk around the more massive and hotter star, the Gyner. The Gyner is about twice as massive as the donor, since this star is embedded in a relatively cool, about 6,000 kelvins temperature, the disk edge, and optically thick disk, so the spectrum of the star is not observable. The topic of my talk today is the Doppler shift and the profile changes in our observed and spectra. My choice of recent research goals was motivated by unexpected and somehow contradictory results obtained from my earlier analysis, and also the analysis of other researchers. My talk today will be focused on let me say, finding answers to some of my dilemmas regarding Doppler shift of spectral lines and change of shape of the profiles with orbital phase. Sorry. To resolve these dilemmas, I analyzed the behavior of 4 spectral lines, 3 helium lines, and 1 hydrogen line, selected from our high quality spectra observed at different orbital phases at Rosen and Apache Point observatories. Let's go. My first dilemma. So in 2019, Kononov and others published the results of their modeling of the age alpha line profile. The model indicates the presence of a stellar wind of Geiner. The following 2 questions may be asked in this regard. Why would only the Geiner have a stellar wind when the donor also fulfills the criteria for its occurrence? And the second question, can a stellar wind be formed at all when the Geiner is embedded into an optically thick disk? Here you can see the model of Kononov. The green arrows indicate the wind. Let's observe these stars about 2 symmetric orbital phases. The profile of age alpha line at 0.166 phase is here, is a typical for expanding atmosphere, for instance, stellar wind, and it means that it has a P Cygni shape. But the profile of at phase 0833 does not show P Cygni shape. You can see here. We can suppose that maybe it is masked by other effects. But we may wonder whether other spectral lines shows P Cygni shape confirming the presence of stellar wind of Geiner. In order to clarify these issues and these assumptions, I analyzed our observed helium 587 nanometer line profiles at 2 phases, 0.966 and 0.126. I will present here using a simplified animation of these observed spectral lines. But before that, let me talk about the line profile of P Cygni type. You can see here the P signified profile. It consists of absorption component, Doppler shifted toward the shorter wavelengths, and then emission component with its unshifted maximal value. The blue wing of absorption component is elongated toward the shorter wavelengths, reaching the continuum at the so-called thermal velocity. This is here. So some spectral lines lack the emission component. Such a case appears to be with our helium line at phase 0966 phase. You can see. And let me do that mentioned simulation. Here is a absorption component, and here is an emission component, and it's can give this observed spectral line profile. We can assume two extreme situations. Absorption component belongs to the gainer, and the second one that it belongs to the donor. In the case of first assumption, the general shape of the profile should not depend on the orbital phase. Let us see that. At phase 0126, it's obviously that it is not true. In the second case, the emission line at that phase should be shifted to the red, and the absorption one to the blue part of the spectrum. The observed shape of the profile at this phase obviously suggests exactly the opposite direction of displacement of emission component in respect to the absorption one. Therefore, it is not, let me say, not confirmed that the existence of classical stellar wave from Gainer and neither on donor. But there is another rough check of possible existence of stellar wind of Gainer. Namely, we can check it by measuring the terminal velocity, which is one of the global characteristics of the stellar wind of hot stars, OBA stars, for instance. Sorry. So I measure terminal velocity of that helium line, and at 6 orbital phases. You can see the results here, and approximation of the measured values of terminal velocity by a second order polynomial. Green lines are the 95% confidence levels, the approximation. The highest value of terminal velocity is about 700 kilometers per second, and is achieved at phase 0, and the lowest is about 300 kilometers per second at phase 0.5. This velocity range and the corresponding effective temperature range is marked in graph of the correlation between the thermal velocities and the effective temperature. And thermal velocity that would have a gainer and a donor are marked by this arrow here. It is almost apparent that it is very unlikely that the measured thermal velocity origins from the component stars. That is, let me say, another evidence against the existence of a Gainer's stellar wind. If we observe the spectrum formed in structures, let me say, located in the tube of our line of sight, the spectral line shape determined by a hemispherical symmetric outflow from Gainer, let me say stellar wind, at symmetric orbital phases, has to be very similar. That is, the P Cygni component of the observed line profile has to be alike. But what we see on observed spectral lines, here is one orbital phase of these observed spectral lines, and it is another orbital phase which are symmetric in the system. Oh, sorry. So we can conclude from here that these results again don't support the claim of the existence of stellar wind of Gainer. What can be the source of this asymmetry of the observed spectral lines? It could be interpreted by an infalling gas stream as the phase 0.164 and an expanding gas stream at phase 0.826. This can be caused by a rotating thin disk halo in front of the donor, for instance. The possibility of existence of such a gas motion is clearly confirmed by Dmitry Bisekalov simulation of gas dynamics in close binary stars. When the matter of the stream of donor is redistributed in the three parts: the accretion disk, halo, and the circumbinary envelope. Here, these blue areas. So let's go to my second dilemma. So my measurements, different spectral lines, radial velocity of different spectral lines produce significantly different radial velocity curve amplitudes. It span 160 to 200 kilometers per second, with a random error of about 10 kilometers per second. So it is significantly different results. What to say for that? In principle, radial velocities are obtained from the measured position of the spectral lines. However, what we mean by the position of spectral lines when the line profile, as we see, are asymmetric. For example, consider measurements of line position by profile overlapping method using template spectrum. When the object and template line profile asymmetry is very similar, the overlapping their profiles leads to an ambiguous solution. But when asymmetries of profiles are different, the solution is not an ambiguous. Since our lines are asymmetric and their asymmetry change with the orbital phase, the measured position can be weighted by systematic errors. Therefore, the radial velocity obtained from them also too. This may be the reason for the different values of amplitudes of the radial velocity curve obtained by measuring the position of different spectral lines. But that leads me to the third dilemma, whether the asymmetry of our three considered spectral lines can significantly affect the measured positions. That, of course, depends on the degree of asymmetry and the required accuracy. Rayleigh measurements for asymmetry is its bisector. Therefore, I determine the bisectors of our three observed spectral lines. Here are our results. As you can see, the bisectors at one phase are asymmetric in other direction and other than in at other phase. The bisectors change about 100 kilometers per second, which is significant compared to the expected change of their position of about 400 kilometers due to the orbital motion. The asymmetry, as I mentioned, is opposite at two phases. Even in core of the spectral lines and also in the wing of the spectral lines. So it can be concluded that the influence of asymmetry on the measured position of considered spectral lines is significant and may be the cause of large differences in the results of determining the semi-amplitudes of radial velocity curves. Now, let's consider three interesting details in the profile of our three spectral lines, which we observed. And they are marked by yellow rectangles on that slide. And we can find here some interesting features. One is that here it's pointed by IA. It is interesting that the position of that feature is not depend on orbital phase. It stay unshifted. It is most likely formed in the interstellar gas because it is very narrow. But the wavelength of this relatively wide profile spectral line is also independent of the orbital phase. It may be formed in circular binary gas. Therefore, in addition to the asymmetry, the profiles of the spectral lines can be additionally deformed by other spectral lines. The deepest peak of the profile at phase is 0164 and shifted towards the red, while the at phase 0826 toward the blue part of the spectrum. The direction of the displacement and the semi-amplitude of radial velocity curve calculated from the measured displacement of the peaks at two phases indicates its origin in donor. The green value in the parentheses of the accept is the, let me say, the accepted semi-amplitude of airway curve by other authors. So finally, we can get a summary. The presence of stellar wind of the gyre is not confirmed. Instead, we most likely detected at orbital phase that one of a gas flow from the donor, a gas flow toward the donor at that phase. We identified stellar components inspected hydrogen and helium profiles. We find that helium and hydrogen line profile bisectors are practically particularly asymmetric, which vary strongly with orbital phase. And we guess that the line asymmetry introduced systematic errors in airway measurements. And at the end, we can say that for airway radial velocity measurements, we recommend using as less asymmetric as possible and very carefully selected spectral lines. For instance, from the group of metallic lines. And it is the end of my talk. And thanks you for your attention.
Thank you, Professor Istvan, for a nice talk and really interesting cases presented. So as we are all panelists, promoted as panelists, you cannot raise your hand in order to ask question. We have just time for one quick question, comment. You can just unmute yourself and ask the question. Or to post through the chat box.
I have a question.
Yes, please.
Concerning your second dilemma about the fact that different spectral lines produce significantly different radial velocity curve amplitudes. Does the line formation region intervenes? I mean, is it of any influence in these differences?
It could be that line formation region is one of the cause of that.
Because these lines come from different places in the atmosphere, in the stellar wind. So the velocity, which is determined using different lines, is expected to be different.
Yes, of course, but we have to say that the measurements of radial velocity, or better to say, if you choose the spectral line, we suppose that the spectral line belongs to the photosphere of the,
yes,
of the component, and it not formed in regions like stellar winds or very far
mm-hmm.
from the component.
Mm-hmm.
So, and the problem is that
but the photosphere is also large in these very massive stars. Yeah, yes. I mean, it is extended, and
yes, if it
maybe in different geometrical heights, the differences can be produced. Maybe. So the line formation region, maybe I would like to say that it
yes,
influences it.
I would just like to say that it is really nice discussion, so you can stay
yes. Thank you very much.
More, because we have to finish this morning session. And if you like to discuss more about this interesting talk of Professor Vince, please do it now. The next session will start at 13:50.